atomic bombs, nuclear fission, and the God particle. All are known today because of a few well-known scientists and unknown scientists, and they are the reasons we have such amazing pieces of technology. Atomic bombs are made by a chain reaction of neutrons being absorbed by uranium-235, which creates two more atoms, then releases its neutrons to restart the reaction. This is why nuclear explosions are so large. Nuclear fission, on the other hand, is completely different from nuclear fusion and nuclear bombs. Nuclear fusion focuses on the atomic nuclei close enough together to create new atomic. The difference in mass between two particles and reactants is manifested as a release of large amounts of energy, which is why we have nuclear power plants. The God particle is by far my favorite out of the three because it's a 27-kilometer tunnel 300 feet underground and is a particle accelerator. It is used to slam particles into each other at almost the speed of light, 186,000 miles per second. It has been used in cancer treatment and has reached the highest temperature known to man, 9.9 trillion degrees Fahrenheit. That is a whopping 618,750 times hotter than the center of the sun. All of these incredible successes can be given to a few great scientists from a time long ago. Around the year 400 BC, Democritus, an amazing philosopher, adopted the theory of the atom and his mentor Leucippus. The theory boldly stated that the universe is composed of two elements, the atoms and the void in which they exist and move. Democritus hypothesized that the atoms cannot be destroyed or created. They differ in size, shape, and temperature and are always moving and are invisible. He believed that there were an infinite number of atoms in the universe. All matter consists of invisible particles called atoms. He also believed that they were solid and indestructible. He also stated that atoms were homogeneous and different in size, shape, mass, position, and arrangement. Solids are made of small pointy atoms, while liquids are made of large, round atoms, and oils are made of very fine, small atoms that can easily slip past each other. All of these reasons put together easily makes him a worthy candidate of a Nobel Prize nowadays.
Aristotle. What can be said that has not already been said? He was a brilliant and bright philosopher from ancient Greece. He lived his life asking for questions and not fearing the repercussions. He was truly amazing for his time. No one can ever even compare. When the atomic theory was discovered, Aristotle did not believe in it. He believed that all substances were made of fire, water, air, and earth. He taught his beliefs, and he was so well known for his teachings, most believed him to be right. Shortly before Aristotle's death, Alexander the Great fell out of power in Athens, and the new government associated Aristotle with Alexander the Great. This caused Aristotle to be forced to flee.
By far, Dalton's most influential work in chemistry was his atomic theory. Attempts to trace precisely how Dalton developed this theory have been proven futile. Even Dalton's own recollections on the subject are incomplete. He based his theory of partial pressures on the idea that only like atoms in a mixture of gases repel one another, whereas unlike atoms appear to react indifferently toward each other. This conceptualization explained why each gas in a mixture behaved independently. Although this view was later shown to be erroneous, it served a useful purpose in allowing him to abolish the idea held by many previous atomists, from the Greek philosopher Democritus to the 18th century mathematician and astronomer R.G. Boscovich, that atoms of all kinds of matter are alike.
Goldstein studied at the University of Breslau, now in Wrocław, Poland, where he received a doctorate in 1881. His career was spent at the Potsdam Observatory. He was primarily interested in electrical discharges in moderate to high vacuums. In 1886, he discovered what he termed Kanalstrahlen, or canal rays. He also called positive rays. These are positively charged ions that are accelerated towards and through perforated cathodes and evacuated tubes. He also contributed greatly to the study of cathode rays. In 1876, he showed that these rays could cast sharp shadows and that they were emitted perpendicular to the cathode surface. This discovery led to the design of concave cathodes to produce concentrated and focused rays, which become fundamental to numerous experiments.
In 1897, Joseph John Thomson states that cathode rays were composed of previously unknown negatively charged particles, which he calculated must have been even smaller than atoms themselves. He is also credited with finding the first isotopes of a stable, which is non-radioactive, element as part of his exploration into the composition of canal rays, positive ions. His discoveries led to the development of the mass spectrograph.
Over the course of 3 experiments, J.J. Thomson discovered the existence of electrons. He did this by using a cathode ray tube, which is a vacuum-sealed tube with a cathode and anode on one end that creates a beam of electrons traveling towards the other end of the tube.
To add, Robert Millikan played his role in the new discoveries of the atom. Around 1909, he determined that the charge of an electron was 1.602 times 10 to the negative 19th coulomb, and the mass was 9.11 times 10 to the negative 28th grams. The coulomb, symbolized C, is a standard unit of electric charge in the International System of Units. It is a dimensionless quantity sharing this aspect with the mole, a quantity of 1.
The oil drop experiment was performed by Robert A. Millikan and Harvey Fletcher in 1909 to measure the elementary electric charge, or the charge of an electron. The experiment entailed observing tiny electrically charged droplets of oil located between 2 parallel metal surfaces, forming the plates of a capacitor. Now we can't forget about yet another important scientist, Ernest Rutherford. His research proved that nuclear transmutation of one chemical element to another, and he has proved the difference between alpha, a helium nucleus emitted some radioactive substances. An example would be when uranium becomes thorium. Rutherford's gold foil experiment proved the existence of small, massive center to atoms, which would later be known as the nucleus of an atom. Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out their gold foil experiment to observe the effect of the alpha particles on matter. Niels Bohr came into play after he developed an explanation of atomic structure in 1922. His explanation of atomic structure underlies the regularities of the periodic table of elements.
While Niels Bohr developed an explanation of atomic structure in 1922, Louis de Broglie made strides in science in the following year. In 1923, Broglie had discovered that electrons had a dual nature similar to both particles and waves. Louis de Broglie was a French physicist born in 1892. He would later become a world-acclaimed physicist for his discoveries in physics and his groundbreaking work on quantum theory. 1924 is when he would finish his work on discovering the wave nature of electrons and suggested that all matter have wave properties. In another addition to science, Erwin Schrödinger continued to make great links in science. He viewed electrons and observed they were continuous clouds and introduced wave mechanics as a mathematical model of the atom. The quantum mechanical model represents where the cloud is most dense, where the probability of finding the electron is highest.
Under the influence of Ernest Rutherford, James Chadwick discovered a neutral atomic particle, or the neutron. He came across this by bombarding beryllium atoms with alpha particles, uncovering an unknown radiation which is now known as the neutron.